Hi, welcome to this next tutorial, Integration 2, where I'm going to be looking at definite integration. Now I'm assuming you've looked at the previous tutorial, Integration 1, where I introduced you to this sign here, the integral sign, where we looked at integrating some function of x, had terms of the form ax to the power n, and constants in, and I showed you how to integrate them. So if you're unsure of this, do go back and check that video out. And we found that we got some solution, some function of x that was different from what we had here. And I've called it capital F of x. Now what I want to do in this one is introduce you to definite integration, and that's when we've got something called limits. I'll put one of those values here, we'll call it a, and we'll have the other limit up here at the top, b. A and b are generally numbers, and what this means is that we integrate f of x in the usual way as we did in the Integration 1 tutorials, and when we get our integral here, this time we put some square brackets around it. Okay, and I'll show you what this means in a moment, and we write our limits a and b on the end here. And so what this means is that we next go on to put b in place of x, we work out f of b in other words, and then we subtract f of a. So you get this result here, okay, f of b minus f of a. So why do we have definite integration? Well, it has many applications, and we'll be looking at this as we work through the videos. One of the common applications is in working out the area underneath a graph, bounded by the curve to the x-axis. And when you're doing something like this, and I've got an example of a graph here, f of x is x squared minus 6x plus 10. If we integrate this between x equals 1 and x equals 4, we will get this area. So that is one application of applying this result. Another one is what we call volumes of revolution, and we'll look at these in further videos. That's when we take, say, this shaded area here, spin it about the x-axis, and it generates a solid, something like this, okay? And we call this a volume of revolution. And we use definite integration to work out volumes like this. There's a formula for it. That formula is volume equals pi times the integral of f of x all squared integrated with respect to x. And it would go between the limits x equals 1, x equals 4 if we were to revolve that shaded area around the x-axis. But we'll be covering volumes of revolution later on in a further video. In this video, I'll take you through this question. We'll get to work it out at the very end, okay? So let's just move on. We'll have a look then at this integral here, just to demonstrate this idea. We've got to integrate 4x cubed with respect to x. Now if you integrated this in the usual way, remember we add 1 to the power, that'd be 4x to the power 4, and divide by that new power. So it'd be 4x to the 4 over 4, and don't forget the constant of integration, c. Now if I had some limits on this, okay, let's just put in some limits. Suppose I had x equals 1 here and x equals 3 here. Then I would have to put this in square brackets, okay, with those limits in from 1 to 3. And we say that we're integrating 4x cubed, by the way, from 1 to 3, not from 3 to 1. We go from the lower limit to the higher limit, okay? So in this one, we're integrating from a to b, regardless of what the size is of those two numbers, okay? So just give you a note on that. We're integrating between 1 and 3, not between 3 and 1, all right? Now in this example, I can see that those 4's cancel one another out, so it'd be quite good to take that opportunity. And so we're left with x to the power 4 plus c, going from 1 to 3. So that's our result there. Now we substitute the 3 in for x, and we subtract what we get when we put the 1 through for x. So if we do that, we get 3 to the power 4 plus c, and then subtract 1 to the power 4 plus c. And working that out, we end up with 81 plus c for the first bracket, and I've removed the negative across these two terms, so we get minus 1 minus c. Notice that those two c's cancel one another out, and we're left with 81 minus 1, which is 80. Okay? Now, because these c's cancel themselves out, they're always going to cancel themselves out whenever we do an integral. If we write it in here, plus c, you're going to get it in the first bracket, then you're going to be subtracting it in the second square bracket. So what happens is that we don't really bother writing that constant of integration c when it comes to using definite integration, integration with limits. So from now on, I'm going to assume that you know that, and I'm going to leave out that constant c. Okay, so I've got another question for you to look at. This one. Integrate x squared minus 3 between x equals minus 1 and 2. So I'll give you a few moments just to pause the video. When you come back, as usual, we'll run through the question. I'll take you slowly through. You might want to fast forward just to check your answer. Okay, welcome back then if you had a go. So we set up our integral, x squared minus 3. Don't forget we've got a couple of terms here, so make sure you put that in brackets. We're integrating it with respect to x, and we're integrating between minus 1 and 2. So the minus 1 goes on the bottom, okay? That's like following this note up here, integrating between minus 1 and 2. So just integrate the x squared, that's going to be x to the power 3 over 3. Integrate the minus 3 and you're going to get minus 3x. Remember, we can ignore the constant of integration plus c. So we've got this result. Substitute 2 in first of all and subtract what we get when we put minus 1 through. So we sub in those limits and get that result there. It's just a question of evaluating each of those terms, and you can see I've done it here, and just grouping them up together, and it turns out it equals minus 6. All right, so hope you're able to get that one if you had a go. All right, well done. Let us move on now. Let's see what we've got next. Well, you can get definite integrals that become equations, like this example here. Solve this integral going from 0 to a of all of x minus 5 integrated with respect to x. We're told that the result is minus 12. So when it comes to solving this, we're out to try and find that value of a. Well, in order to do this, what I'm going to do is copy down that equation again. Here it is, okay. And then I'm going to integrate the x minus 5. So integrating x minus 5 is going to give us x squared over 2 minus 5x. Between the limits now, 0 to a, and it equals minus 12. All I need to do now is substitute a in, subtract what we get when we put the 0 in, and equate it to minus 12. So if you do that, you're going to get this result here. I can now multiply through by 2. That will give me minus 24 down here and minus 10a there, and rearrange it by adding the 24 to both sides. So doing that, you're going to end up with this quadratic equation that equals 0. And we would factorize this. Factorizing it, nice easy one, gives us these two factors. Put each of those factors equal to 0, leads on to a equaling 4 or a equaling 6. Okay, so there's our solutions to that equation. Now I've got an example for you to try. It's this one here. Got to solve this equation for a. I've made it a little different. Okay, you'll see that in the limits here I've got a and 2a. We're integrating 3x squared minus 4 with respect to x, and it equals 59a. So I've got quite a few a's distributed over here. And a, by the way, doesn't equal 0. So have a go at this. Give you a few moments then to pause the video. When you come back, we'll run through it. Okay, welcome back then if you had a go. Do fast forward as usual if you want to check your answer out quickly. Okay, so you integrate the 3x squared minus 4, should get 3x cubed over 3 minus 4x, okay? Between those limits, a to 2a, and it equals 59a. I noticed that these 3's cancel, so it's a good idea to cancel those. So we'll cancel that and simplify. We end up with x cubed minus 4x then equals that 59a between those limits. Sub in those limits and you've got this equation now. Let's clean this up, and what we end up with is this equation. Okay, you'll notice I've taken 59a from both sides. So if we group up like terms and simplify it, we're going to end up with 7a cubed minus 63a equals 0. And to solve this, we would factorize it, okay? Pull out 7a as a common factor, all right? So if you pull out 7a as a common factor, you're left with a squared minus 9 there. So either a would equal 0 or a squared minus 9 would equal 0. Well, we know a can't equal 0, we're told up here, so it must be the a squared minus 9 that equals 0. And if that's the case, then a squared would equal 9, and we can take the square root of 9, and we end up with a equaling plus or minus 3. All right, okay, so hopefully you're able to get that one. So that's solving integrals, definite integrals, where you've got an unknown, say, in the limit there. Okay, right, let's have a look at another idea. Now I've got another integral here that you might like to try. The integral from 1 to 3 of 5/3 x to the power 4 with respect to x. It's a good one to try, it's fairly quick. But when you come back, okay, what I'd like to do is just show you a few other points about this type of integral. Okay, welcome back then if you had a go. So let's see how you got on. Well, the first thing I'm going to do is pull out the constant 5/3 out the front. When you've got something that's a common factor, you can do this, and it does make the integral a lot easier, as you'll see. You don't have to pull the 5/3 out. I could have left it in there, but it's a good idea to take that opportunity to pull that out the front. Now then, that means we've just got to integrate x to the power 4 with respect to x. And if you do that, you should find you get x to the power 5 over 5. And that means we can simplify this. These 5's cancel. Okay, so if you do that, you're going to end up with 1/3 now out the front, just x to the power 5 inside these square brackets with those limits 1 and 3. So when it comes to working this out now, substituting 3 in, 3 to the power 5 minus what you get when you put the 1 through, minus 1 to the power 5. So it's going to look something like this calculation. And if you work that out, you end up with 1/3 of 243 take away 1, which simply is 242 thirds. Now think what would have happened if I had kept that 5/3 in there. The 5's would have still cancelled, but I'd have had x to the 5 over 3, or 1/3 x to the 5. And that would have meant I would have had a lot more fractions in here, a couple of fractions, which although still not that hard to work out, just would have kind of complicated the thing. So hopefully you can see that by pulling out a constant, if it's a common factor, out the front of your integral makes it generally a lot easier to work with. So that was one of the points that I wanted to demonstrate there. The next point I want to demonstrate is what happens if we do this integral. It looks the same, 5/3 x to the 4, integrated with respect to x. You'll notice I've swapped the limits around. We're integrating from 3 to 1, okay? We're not integrating from 1 to 3, we're integrating from 3 to 1. What do you think our result will be? Well, let's just see, okay? You might want to pause the video at this point, but I'm not going to just hold it up, okay? We're just going to work through it, okay? If you did that, you're going to have exactly the same as what we did through here, okay? As you can see, all the way down to this step here. Only this time I'm putting 1 in first of all as my limit, as you can see here, and subtracting what we get when we put the 3 through. So instead of having 243 take 1, we now got 1 take away 243, and it gives us a negative value. Okay? So the point I really want to draw your attention to is this result here, which you might want to use on some occasions, okay? I'll leave it up to you. You don't have to use it, but sometimes in further tutorials you might see me using this result. And that is that if you're integrating some function of x with respect to x between a and b, it's exactly the same as the negative of integrating f of x with respect to x, but only the limits are going from b to a. We switch them round, okay? Now, if you want a proof of that, it's very simple, okay? I've just got it here. If I was to say let I equal this integral, I've only done this purely to save me room, but if I was equal to this integral of f of x with respect to x going from a to b, then if we integrate it, we get some function of x between those limits. And we've seen that we substitute b in first and subtract what we get when we substitute a in. So we get f of b minus f of a. And if I pull out a minus sign in front of some square brackets here, that's exactly the same as minus all of f of a minus f of b. And f of a minus f of b would be the result of doing minus all of f of x between b and a. In other words, the negative of this integral of f of x with respect to x going from b to a. So hopefully you can see this result proved. Okay, so moving on then, I did promise that I would go through this question that I showed you at the start of the video. That is that we can use definite integrals to work out area under a graph. If you've got a curve and you're looking for the area bounded by the curve down to the x-axis between two lines, two vertical lines, x equals a, x equals b, then it can be shown that that area is given by the integral of f of x with respect to x going between x equals a to x equals b. And we've got this graph here of f of x equals x squared minus 6x plus 10. So what we've got is this question here, to find the area then bounded by this graph, the x-axis and the lines x equals 1, x equals 4 as shown here. So you might like to just pause the video at this stage, have a go at it, okay? And as usual, when you come back, I'll take you through the work solution. Okay, welcome back then. Let's see how you got on. Do fast forward if you want to check your answer. Anyway, the area is going to be equal to the integral then of our equation of the curve between x equals 1, x equals 4. Integrate each of these three terms then, and you should get this result here. We can now cancel the 2 and the 6, okay, that will make it a little bit easier. It gives us minus 3x squared there. So we need to put our values in. 4 first, subtract what we get when we put the 1 in. That's our result here. And evaluating all the terms, you should have got this. And what's it going to equal? 6. Okay, so I hope you're able to get that one. Now, technically, I would say that's wrong, because we're working out an area here. An area should be measured in square units. So I like to put square units on the end there. Or you could write units squared if you wish. Now, some people will argue you don't need to write that. You generally don't necessarily see it written in textbooks, and on exam papers you don't necessarily see that given as the answer. But I would encourage you anyway to put square units, because, as I say, it's an area. And you could look at this sketch here, and you'll notice that if you count the rectangles, I know they're not squares, that's purely because I haven't got the scales exactly the same on the axis. But nonetheless, if you count these rectangles, you'll see that there's 1 whole 1, 2 there, 3 there, almost 4 there. And if you look at these extra little bits, you should be able to visually see that you've got roughly what would appear to be 6 square units. So that just is a guide to show you what is actually happening. Okay, well, that brings us to the end of this particular video, Integration 2. In Integration 3, I'll be extending this work on areas of graphs. So I'd like to think that you take a look at that. And also in the description below the video, you should notice other links to questions that you can practice further on definite integration. Okay, so good luck with that, and hopefully see you in another video. So thanks for watching. Bye for now.